Hey guys, so this is going to be the last video on gravitation, and the final thing we're going to look at is orbital motion. Now this is quite good because, no pun intended, this brings us full circle in this topic. We've started off looking at circular motion, we looked at fields and gravitation, and now with orbital motion, basically all we're doing is we're linking back to circular motion, but for masses under gravity, so masses experiencing some gravitational force. So it's quite a nice little link that we've got back to the beginning. So let's start off by considering what circular motion is. Now, circular motion happens, we said, when you've got something which is experiencing some centripetal force, F, towards the centre of a circle. And what that does is it gives it a change in velocity. Obviously it's accelerating round in a circle, but that force, because it's at right angles to its linear velocity v, it doesn't actually change the magnitude of its velocity. All it does is it drags it round that circle, so we've got a constant change in linear velocity as this body moves round the circle. And we said that it's always at right angles. So circular motion occurs when we have some centripetal force, F, which is centred on the middle of this circle. And we said we arrived at this equation. I think we did sort of a loose derivation of this. I think I linked to a video about it. But that force is equal to mv squared over r. So for this mass here, this body will go around in circular motion if it experiences a force equal to mv squared over r, where r is its radius of this circle, and v is the linear velocity, which of course doesn't change. Now, that's very well and good, and we talked about examples like swinging a bucket around your head, that kind of thing. In that case, the force comes from the tension in the string. There are lots of other cases, and whatever the case is, for circular motion you do always have to have this centripetal force, and it's always there. It doesn't matter what it is. So the interesting thing now is, well, talking about the case with the bucket, what if we now replace tension with some other kind of force? It can be any kind of force whatsoever. So let's now say in the middle of this circle we have a massive body, m. Now we know, because our mass here, little m, is now going to be within that gravitational field, it is going to experience some force as well. And the force it's going to experience is going to be due to Newton's universal law of gravitation. So it's going to experience a force like this. And actually, this force and this force are exactly the same thing. So what I can actually do is equate them. I can say, well, the force, the centripetal force that this mass experiences is literally just the force due to gravity, because it's in the gravitational field of this bigger mass, m, here at the centre of the circle. So now we have two forms of the same equation. So some interesting things we can look at. Equating these now, the first thing we can see is that the m's cancel. So orbital motion actually is independent of this mass m. We don't care about your mass, and again that makes sense because we're operating within a potential field, a scalar field. So we shouldn't be surprised that it doesn't matter what my mass is. And actually, if you think about this circle, this orbital circle, is actually an equipotential line. Again, so it doesn't matter what my mass is. So that's the first thing. Another thing we can look at is we can rearrange this to get our velocity squared. And the sort of little trick that I'm going to use here is, the first thing I'm going to do is say that my F centripetal is equal to my F due to gravity, but I'm going to be looking at the magnitudes of those forces, and the reason I'm going to say that is because I want to get rid of this negative. Another argument for getting rid of this negative is because there'll be some Newton's third law, so there'll be equal and opposite forces. So whatever this force F here is acting on this body, there'll also be an equal and opposite force acting here, so that negative will cancel out anyway. So doing that, obviously we drop the m's, that leaves us with v squared over r is equal to the magnitude gm over r squared. And if I bring my r over, I get v squared is equal to gm r over r squared. So this r cancels with the squared. And finally, my linear velocity now is just given by root gm over r. Lovely. So now we know what my orbital velocity is. So if I get rid of all of this, so all we did is we equated those two forces. So by equating centripetal force for a mass m at velocity v with gravitational force a la Newton, my boy, we arrive at this equation for linear velocity. So this is just equal to the linear velocity experienced by my mass here. And if you're keen-eyed, you might spot that actually this is root times my big V, so it's the square root of my potential, or minus my potential. There are reasons for that which I won't go into, but the thing to notice is it's probably going to be because of this equipotential line down here. So the first thing to see then is as I move my mass away, so I might fire some thrusters so that my mass ends up on a different orbit up here. That means the radius is going to be larger, so if this r increases, this decreases, so this v is going to be, if I call this v prime or v dash, this v is going to be less than the v it had over here. So changing your radius will actually change your speed. The closer you are to the planet, so the closer your mass is, the faster it goes, and vice versa. Which may be counterintuitive, but the way you want to think about this is the closer you are, the bigger the centripetal force. The bigger the centripetal force, the quicker your circular motion is going to be. Okay, so I'll just copy this down and we'll consider something else. So that's really nice. We now know at any point what our orbital velocity is going to be. So another thing to consider is, so I'll get rid of this. This is all we need to know for now. Obviously, at this point, it's going to be at some radius r from the centre of mass of this system. So another thing to consider is, well, what energy does this particle have? Because obviously it's moving, so if it's moving it's going to have some EK, and that's just going to be equal to half mv squared. And because it's within my gravitational potential field, it's also going to have some EP, which is going to be equal to mv. So just like when we throw a ball up in the air, if I throw a tennis ball in the air, at some point we know it's going to have some GPE because of its height, and we know it's going to be moving, so it's going to have some EK as well. It's nice to consider the energetics of this problem. So what is the total energy of my mass that's orbiting? So these two equations really are quite clunky because they're not really compatible. They've got two different terms. I've got velocity here and I've got big V potential here. So we want to get them in terms of the same thing. But we've just said actually that the V is equal to this. It's equal to this guy up here. So if I substitute that in, V squared just becomes G big M over R. I'll put that in brackets. And V down here, again, becomes minus Gm over R. So, sorting these two equations out, my kinetic energy actually now becomes a half Gm over R, and my potential energy becomes minus, because obviously remember it's always negative because it takes some work to escape. I'm going to have to put work in. That's going to be Gm over R. Sorry, forgot my M up there. So my total energy, so total orbital energy, is just the sum of those two things. It's just the sum of the two energies, so I'll call that E. And that's going to be Ek plus Ep. My Ek is a half Gmm over R minus Gmm over R. So I've got a half of something. This term is identical to this term, so I've got a half minus a whole. So my total orbital energy now, E, is just equal to minus a half Gmm over R. So at any point in my orbit, no matter what the orbital radius is, I have some amount of energy. And you'll notice by looking here, it's always negative. And you shouldn't be surprised by that. Why shouldn't you be surprised? Well, again, it comes down to this idea that I'm going to have to escape. So I need to leave. If I want to leave the gravitational influence of this planet, I'm going to have to put in some energy to escape it. So it's always negative. My total energy depends on R. It also depends on the product of the masses, which we shouldn't be surprised by. This R tells us that the further away we get, so increasing R, is going to make this number smaller. So increasing R, we have to be careful how we word this. If I make this number smaller, it's actually getting less negative. So I'm starting to escape that potential well, if you like. If you remember the potential well, increasing R, I'm getting closer and closer to having zero energy. So what else can we talk about? We might be interested in, so if we consider this whole equation up here, we might want to consider what happens when we change our orbit. So say if we go to a small orbit to a larger orbit, so I'll just copy this down, we'll talk about that quickly for a second. So one thing particularly rocket scientists are interested in, and the equations do become more complicated, what happens if I start off here and I move up to a higher orbital radius? So this is my original radius and I move up here. So R is increased. So we can get everything we need from this equation. So we're increasing R, which we've just said means that our total energy becomes less negative. So E increases. Yeah, less negative, so it increases. That's the weird kind of thing you've got to be careful of here. Okay, so what happens to our other energies? What happens to our kinetic energy and our potential energy? So again, increasing R, if we just look at the potential energy term, that's minus Gmm over R. So increasing R means that our potential energy is also going to increase. It gets less negative. So that is also going to increase. And both of these are because it gets less negative. You have to remember that. And finally, increasing R is actually going to decrease my kinetic energy. yeah, it's a positive number, so r gets bigger, this term gets smaller. So if ek decreases, that means my v decreases. So going to a higher orbit actually slows me down. And vice versa, if I drop down to a lower orbit, my ek is going to increase, which means I speed up. I'm going to move through some potential to a lower equipotential, so my potential energy is actually going to decrease, it's getting more negative, and therefore my total energy decreases, it's more negative. So that's energy. And I'll just talk about one more thing before we finish, because this has come up quite a lot in the last couple of weeks. We've talked about this a few times, so I just want to make this absolutely clear. A lot of the time we get questions which say something like this. I've got my little dude on a planet here. You might be on Earth or Mars. They want to know what speed do I have to move at, so what initial velocity do I have to have here, v, such that I can escape. So basically, I'm starting off at this position and I want to get to r equals infinity. I want to completely escape the gravitational influence of this planet. So the question is, how much speed do I need? And what they're actually talking about is, what is my escape velocity? And the mistake people often make is they do this, they go back to this circular motion, they start deriving, well, I know the force is acting, so what force do I need to equate such that I get this v term here? But actually, remember, that's just your linear velocity. This is the speed to keep you going round in a circle. If you want to know your escape velocity, really what you want to consider is how much potential energy is there at this point, and therefore how much kinetic energy do I have to convert such that I completely escape this well. So I often think about this as being an energetic problem in a gravitational well. So you start off at the surface of the planet, down here near the bottom. You want to get from this position all the way up to the axis. If you get up here, you're effectively out of the planet. So this might be v against r. This height would be delta v, and remember, the energy, EP, is just m delta v, where this guy has some mass. So we need to consider the energetics of the problem. So it's quite straightforward, it's not too difficult. How much energy do I have down here? Well, really, let's consider potential. So down at the surface of the planet, I have some potential, which is minus gm over r, and I want to escape to infinity where v is equal to 0. So my change in potential is actually going to be this minus this. So I'm going to use up gm over r. How much energy is that in total? Well, that's just EP, which is m delta v, so that's gmm over r. That's how much energy I have to overcome. But we want to know, so I'll just put hats on these legs, put some serifs on so we know the difference. We need to know how much energy do I have to start off with to be able to do that. And the energy of choice is obviously going to be kinetic energy, because we're going to be, burning fuel or whatever to escape that. So we're just going to use our standard mv squared, or half mv squared. And it's a case of just cancelling down. My escape velocity, again, is independent of m. Okay. Again, we shouldn't be surprised, because we're escaping the field. This well is independent of mass. So that gives me gm over r is equal to half v squared. If I multiply both sides by 2, I can bring the 2 over there. And then finally, square root both sides, my escape velocity, so ESC, is just the square root of 2gm over r, which actually, again, if you spot, is actually equal to just 2 big V. So it's twice, the square root of twice the potential at the surface. So again, it makes sense that it's linked to energy. So that's how you derive in an exam how to get your escape velocity. Again, don't remember this equation, and don't try and remember this equation. Learn how to derive them. If you do that, you're golden. You'll understand it much better. So that's it, that's gravity. We've come full circle, which means next time, the next video, we'll take a look at oscillating motion. So I'll see you there. Thank you very much, guys. See you later.